Welcome to the third and final part of this mini-series about base units, derived units, and homogeneity of equations. What I'd like to discuss now is what makes an equation correct. Okay, so for an equation to be correct, it needs two very particular properties. Number one, it needs to be equal in terms of the amounts. Okay, that is presented on the left hand side and the right hand side. So I mean, if the answer to an equation is say 78 kilograms, then that's on the left hand side. That needs to be equal to 78 kilograms on the right hand side. So it needs to match in terms of values, but it also needs to match in terms of units, okay, in terms of base units actually. So one determining factor in proving an equation correct is if it is homogeneous in terms of its base units. And I'm saying base units and not just units, because you might have an instance where you're given, I mean, the answer, left hand side and right hand side would be 78 newtons is equal to 78 kilogram meter per second squared. And just by looking at that, you'd say, oh, okay, that doesn't match. All right, so those are not really equal, but in fact they are, because this is the Newton given in terms of base units. Okay, so many times, as far as defining properties of a correct equation, we're going to say, listen, have both in terms of their base units, because then they will always match up if the equation is correct. So one of the exercises that is, one of the calculations that comes out quite frequently in exams is actually to prove whether an equation is correct or not. And one way of doing that, well, at least you'd get a part answer. One way of doing that is to check for its base units on the left hand side, on the right hand side, and see whether those two match up. Then the equation might still be incorrect if it gives you an incorrect value, an incorrect number, okay, on one side to the next. But the very first step is to check that the quantities you've got on the left hand side and the quantities you've got on the right hand side actually are equal. Okay, so let's just work a couple of just two examples here, and then there's the worksheet linked in the description. Just download that and work a couple more questions on your own. You've got full solutions to that provided for as well. And we're on page 18 of the notes. All right, we're on page 18 of the notes. Again, if you haven't downloaded them yet, please do so. If you haven't seen the first two parts that come before of this video, I'll have a link up top, and please go check those out first. So, first equation that we are going to check to see whether it's correct or not is going to be Einstein's very own E equals mc squared. And yeah, obviously, well, hopefully this is correct, and it should be. So what you'll do in this case, if you want to check for homogeneity, then you're going to just structure your work with the left hand side and the right hand side. And what you're going to do is come up with the units for the quantities that are presented on the left hand side of your equation, and here do the working to come up with the units, base units actually, for what you've got on the right hand side. Okay, so left hand side we've got energy, as we've been doing all along, or rather in the previous video. Get an equation for energy. Any equation will do other than the equation we've got presented here. Okay, because technically we're checking whether this equation is correct or not, so we can't really use it because we shouldn't know whether it's correct or not. Okay, so we're going to go with another equation that we know is correct. Okay, so say for example I'm going to choose again potential energy. All right, trying to use same equations we've used in previous videos to have some kind of continuity here. So mgh, mass and height are both base quantities. Okay, mass and length, there are two of those 7 base quantities. So acceleration due to gravity, acceleration is what we need to open up there because it is derived. So I choose another equation for it. Velocity and time. Time is base quantity, so it can't be broken down any further, but velocity can, because it's combining, or rather it's quantity, it's a derived quantity that has come up from combining distance and time. So distance and time, I need to fix that, move right hand side to the right hand side actually. Yep, there we go. Okay, so units. These are base quantities, mind you. These are both base quantities, so we can't break them down any further. So we can start converting to units. Okay, so that's going to be meters, time in seconds. Moving on to this side, this is going to be the unit for velocity. Meters divided by seconds, which is in the denominator, next to the unit for this new time. Okay, that we got from this equation. So there we go. That will give us meters per second squared, which we know is the unit for acceleration, so we know that we're working things out correctly. Writing that down under the symbol for acceleration there, height is given in meters. I should, if I'm really keeping up the color schemes there, I should write this down in purple, so that goes with mass, meters. Mass is in kilograms. All of that is multiplied to one another. So the units we've got on the left-hand side, which are the base units for energy, okay, is kilogram meters squared divided by seconds squared. Now, having gotten to this, we know that if this equation is correct, if Einstein is correct with this equation, which he should, right-hand side should give us those same base units. Okay, and if we do get the same base units, then we're one step closer to determining whether the equation is correct or not. Okay, so mc squared is what we've got on the right hand side. Again, same process that we've been doing here. We're going to look at those quantities and decide if there is any one of those quantities that is derived, okay, and therefore it can be broken down further. Mass is a base quantity, so it can't be broken down further, but c, there is for velocity of light, okay? We give it the symbol c because it was, someone defined the speed of light as celeritas, which means swiftness in Latin, okay? So that is where the c symbol came from, but at the end of the day, it's still velocity. It's velocity squared, actually, okay? So we need to do something interesting with it now. Velocity to the power 1, that is given by distance on time. However, our velocity here is squared. So what I'm going to do to my equation is I'm saying, listen, I need velocity squared. Whatever I do to the left-hand side, I do to the right-hand side, otherwise the equation will no longer be equal. So if I am to come up with the units here, these are both base, so we don't have to break down any further. But S is meters, time is in seconds, but both of them are squared. So essentially what we've got there is meters squared divided by seconds squared. So that is what I'm going to write down under c squared. Okay, so meters squared, seconds squared, and then I've got my mass there, which is given the unit kilograms. So the units, the base units I've got on the right hand side is kilogram meters squared all over seconds squared. And as we can see, those two match up. Okay, so our final answer is going to be the base units on the left hand side and right hand side are equal. Therefore, the equation, which is that E equals mc squared, is homogeneous in terms of base units, in terms of its base units. And that will be my final answer. Okay, it's not just about the calculation, it's about the conclusion that I come up with from such a calculation. All right, so that is the first calculation that you've got on your notes. I've given you a second example, which I'm going to work out very quickly right now, and then it's up to you to do a couple of calculations from the worksheet I've linked in the description below. So, second equation, it's still a correct equation, okay? I mean, I'm trying to choose simple equations at this stage, since you are, well, most probably if you're still here watching this video, it's something you maybe need help in. So I'm trying to not complicate things too much at this stage, very early on. So V equals F lambda. It's again something that is generally covered in previous levels of physics. It defines the velocity of a wave of a particular frequency and particular wavelength. Now, again, if we want to check for its base units, we're going to go with left-hand side. We've got velocity. Choose an equation for velocity. Velocity is equal to distance on time, both of which luckily are base quantities and therefore do not need to break those down further. And we got to our base units on the left-hand side. On the right-hand side, we've got frequency and wavelength. Now, frequency is not one of those 7 base quantities, so we do need to come up with an equation for it. The equation for frequency, which is generally used, is 1 divided by the periodic time. Okay, it's the inverse of the periodic time. Time is one of those base quantities. Okay, so it doesn't have any units. Okay, so it's not even a quantity there. It's just a value. But in the numerator, I do have a unit. So the unit for frequency, the base unit for frequency, is 1 on s, or s to the minus 1. Do I need to break down wavelength? Is it one of the 7 base quantities? Well, essentially it is the length of a wave. So length is one of those 7 base quantities. So I do not need to find an equation for that. Okay. So what we're going to do there is simply copy this down under the quantity of frequency, and there note that I've got meters for wavelength, and therefore I've ended up with a meters per second on the right hand side. The 2 quantities, base quantities, match up. Okay, so again, this time around I'm going to say same thing. Left hand side, or rather base units. Let's explain ourselves well. Base units on the left hand side are equal to those on the right hand side, and therefore the above equation is homogeneous in terms of its base units. It's very important to state that it is homogeneous in terms of base units and not just that it's homogeneous. Why? Because homogeneity only means that both sides are the same. Okay, so they are the same in what? In value or in units. I mean, and you could have derived units and base units. They won't match up. They will only match up in terms of base units.